Okay. And go from current slide. All right, before we get started on that, let's go over just a few announcements. I think you've heard most of these, but if you haven't, I did confirm that we do have a Coach Jefferson here at Lawson, Jonathan Jefferson. He sent this email about a company named No Kid Hungry. It has the company description. The job title is Brand Ambassador. The job description, he lists 2 bullets here. Interested candidates should contact Henry something and other via email, and his initials must be HS, and then there's 7 digits, and at gmail.com. The weekly wages are $350. So if you know anyone that's looking for, sounds like pretty much of a entry-level job that needs a job, they've got a position. So if you want more information, Henry's email is up here. And then I think I told you earlier about the summer research experiences for undergraduates. The middle poster there is last year's poster for this, which looks very much like this year's poster, but I can't find this year's poster, so I'm leaving that one up here. It's a great opportunity. Several universities across the country have these programs. They're sponsored by National Science Foundation. Yeah, National Science Foundation. And they are great opportunities for undergraduate students to participate in research. You learn a lot. They pay you to learn a lot. They feed you to learn a lot. It's a 10-week summer thing from May 17th to July 24th. Experimental and computational materials research. And it's just good all the way around. So if you want, they'll house you if you need housing. Okay. So here's the information. There's websites. There's emails. There's phone numbers. There are all sorts of things. Anything you want to know about it is here. And you can also access this one and others, I think, through Blackboard or somewhere like that. I've seen a posting like that somewhere. So that's off campus. On campus, I think I told you all this last time, they finally, this week, opened student course evaluations. So please do the student course evaluation, because Logan said he had done his, had a few others in other classes. Please do these before you forget, okay? Get them done before the end of the term, okay? Now, more specifically for this course, we are, I think, more than halfway through Chapter 8, okay? So hopefully we'll finish Chapter 8 today, okay? Then we will have the test on Chapter 6 today. And then some of you may even get to go home a little early today, because that's all we've got to do today, is finish Chapter 8 and do the test on Chapter 6. Okay? All right, with that, if you've got the formula and equation sheet for Chapter 6, have that ready. If not, be getting it ready. All right. Now, Tuesday, I'll be returning every lab and every test that I haven't returned already, which is a whole bunch of them. What does that mean? I need all of your labs and tests completed before the beginning of class on Tuesday. Okay? Please get those done and turned in before Tuesday at 3:15. All right? Any questions on that? Please get those done. So, while y'all are eating pizza, and the last I heard, 2 cheese, 1 pepperoni, and 1 3 meat. Is that right? Any changes, additions, deletions, corrections? You okay with that? All right. While y'all are eating pizzas, I will be returning those labs and tests to you. That means you have to have them done before class on Tuesday. Once we get those distributed, we will do the lab for Chapter 8. I don't think it'll last you a full 2 hours, but you certainly have at least 2 hours to work on. Once you finish that, we'll have the test on Chapter 8, because we should finish Chapter 8 today. And if we do, then the Chapter 8 test will be after you finish lab for Chapter 8 on Tuesday. And after that, you're free to go. Okay. Now, if some of you want to take your final exam on Tuesday, that'll be okay. I know Mark is graduating and he wants his grades in ahead of time, so you'll know. And somebody else, I think, asked me something that they had a trip out of town or something. So I'll give everybody the option of taking it anytime after we finish the Chapter 8 test. That could be Tuesday, it could be Wednesday, it could be Thursday. I'll even give it to you Friday morning, but that will have to be on the Birmingham West Campus. Time out, I forgot something. Let's back up to this week. Tomorrow morning, normally I'm on the Birmingham West Campus for office hours 8 to 12. Tomorrow I've got a doctor's appointment at 9:20, so I can be on the Birmingham campus from 8 to 8:40, but I'm going to have to leave somewhere around 8:40, maybe 8:45, to head back to Birmingham, Kirkland Clinic for my doctor's appointment. So I won't be there but 40 or 45 minutes at the most, okay? Then I'll be heading back. Now, if the doctor's appointment, what it is my annual physical, which was originally scheduled for last spring, and he had to cancel for some reason. His office called and said they had to reschedule. I said, okay, when? They said either September, October, November, something like that. I said, what? And then they were going to give it during the week. I said, no, I need it on Friday. Oh, well, then that'll be December 6th. Okay, so that's why it's this Friday. Okay, it's almost a biannual physical, but now it's an annual. Now, if he wants me to have lab work done, blood work, anything else, test or anything, my appointment could go most of the morning. Okay, those extra things take extra time. But if it's just in his office and he said, yeah, good to go, I might be able to get back to the Birmingham campus. I don't think I'd get there much earlier than 11, but if I can get there that early, I'll stay another hour, okay? However, if they keep me at the Kirkland Clinic until after 11:30, it's not worth time for me to go back to Birmingham. So, I can only guarantee, knock on wood, I'll be there from 8 to 8:45. But, if I can, I'll get back afterwards. So, but don't bank on it. Call first. You have the number on the Birmingham campus. 929-64, whatever. It's on the service. Okay. And my locator card is there. 649, I think it is. All right. So that's Friday. And that's next week. I got up to Tuesday, right? Okay. Wednesday, I'll also be on campus all day long. I'll be on this campus from 8 until 4 on Wednesday. Then at 4, I have to leave and go to the Birmingham East campus, and I'll be there for my physics final, and that's from 4:30 till 6:30. So I will be here 8 to 4 on Wednesday. No other finals, just that, and then the one on Birmingham campus, East campus, 4:30 to 6:30. Thursday, I'll be here on campus from 8 until this class is final, which technically is at 3 o'clock. So if you don't take the final on Tuesday, I'll be here from 3 until 8. So you have a big window to take it on Thursday. If you do take it on Tuesday, you'll be done. Okay, but I will be here. I don't want anyone cramming it in on Tuesday if you need more time to prepare. Okay, so I'll be here 3 until 8. Now, I only stay in the room here probably until 3:30 or so. If no one shows up, then I'll go down to my office, and from the office, you can find me there. Okay, I'll be there from whatever that is till 8 o'clock. Close to 8. I may leave a little early if no one shows up. Now, Friday. This is not tomorrow Friday, a week from Friday. I'll be on Birmingham West Campus, basically from 8 till 3. However, I'll only be in the office from guaranteed 8 to 12. I may be there a little after 12, but graduation starts at 1 o'clock. And sometimes they want us over there an hour ahead. There's no reason for that. Sometimes 45 minutes, sometimes half hour. Whenever they say we have to be there, then I'll leave the office and go over there. Once I'm over there, the only time I'll be back in the office after graduation's over, come back, pick up my stuff, and leave. So I'll only be there for definitely in the office from 8 to 12. Maybe there a little longer after 12, and maybe sometime around 3 when I'm back in the office, but no longer. Now, the following week, the week after next week, Monday is when grades are due. They're due by noon on Monday. So if I don't have everything in Monday morning when I arrive, okay, then I'm putting the grades in. If you're missing something too much, you're getting an incomplete. And then you can come in Monday, Tuesday, or Wednesday, or next term and clear the incomplete. Now, Monday, I'll be here all day from 8 till 6. I have to have grades in by noon. Tuesday and Wednesday, we have duty days. I'll be on campus. The trouble is, I don't know which campus. In the past, they've always let us work in the office on those duty days to get ready for next term, get caught up with everything, get things straightened out, papers, got to clean up after the term. Recently, they started trying to schedule meetings on those days, I think guaranteeing we stay on campus. Micromanagement, okay? If they do schedule meetings, they'll probably be on the Birmingham West campus. And I won't know where or when or how long until they let us know, and they haven't let us know yet. So I wish I could tell you where I would be. I don't know. But give a call to both offices. I should be in one of those two offices. If I'm not, that means I'm in a meeting somewhere else. Okay? So that's Monday, Tuesday, and Wednesday. After Wednesday of next week, not going to be here at all. Not until the new year. So don't bother. The school will be open for a few days, but faculty, we don't get any vacation. That's the only time we got off. Okay. Any questions? All right. Any physical science questions? So you understand what we're doing. Finishing chapter 8 today, test on chapter 6 today, that's it. Tuesday, pizza, returning papers, lab on chapter 8, test on chapter 8. Thursday, final exam. Okay. Any questions? All right. Where we left off last time was about page 216. We did wave mechanics, and we're at the quantum mechanics model. About middle of the way, a little bit below middle of the page on the second column on page 216. Now, here is a lot of what we did at the end last time. I don't know if y'all felt this way, but it sure felt like to me there's a lot of blah, 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 blah. Well, maybe you say alternative and blah, blah. Don't say that. Okay. All right. Now, this may start out sounding like blah, 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 but this is going to really impact what you do in the lab on Tuesday. Okay? The quantum mechanics model. Now, part of the lab stuff we've already done. That was covered last time. Okay? This part, though, is the more time-consuming part of the lab coming up on Tuesday. The quantum mechanics model comes up with these things called quantum numbers. Okay? There's at least 4 different classifications of quantum numbers. These quantum numbers specify the electronic quantum states. Okay? Now, when it says electronic, that doesn't mean like capacitors and resistors and things like this. This is electron quantum states. Okay? Because everything in chemistry is done through those electrons. Okay? The sharing of electrons, the losing of electrons, the gaining of electrons, the pairing of electrons, whatever. So this is why this is here in chemistry. Now here's the visualization. In reality, you can't tell where an electron is. All that we know is where they're likely to be. That's called a probability distribution. And that's why the earlier slides that you had just clouds with little dots on them. I said, that's only 2 electrons there, but you had all these dots. Here's why. This is the probability distribution for electrons. Okay? They don't say what it is. Now, a lot of these are way out there, not very likely, but possible. So they sort of focus in on where they're most likely, and that's your 90% probability volume. 90% of the time, the electron's somewhere in there. Okay? This doesn't sound very specific, does it? All right. This is why it's chemistry, not physics. No, I'm just kidding. It's physics. Also. Now, so the visualization is the wave functions. Remember, we talked about Schrodinger's wave equation. That's the wave functions. And the probability distributions. The electrons are delocalized. We don't know where they are for sure, but we know generally where they are. And we know generally what kind of energy they have. That's what they mean by the electronic quantum states, or electron quantum states. All right. Here comes these 4 classifications of these quantum numbers. Okay? The first one is called the principal quantum number. Okay? Now, that's the main energy level of that electron, the energy level. It's based on the average distance from the nucleus. You know, we don't know where it is, but we know its average distance from the nucleus. That's the principal quantum number. And that quantum number is n. Okay? Now, in reality, you could have n equal 1, 2, 3, 4, 5, 6, or 7. That's as far as I got. I keep holding my book up and I keep forgetting. I have a periodic table here. Y'all can look at this anytime you want to. It's always up there in front. This side is periodic table of the elements. This side shows some more information. Okay? Radioactive isotopes, that kind of stuff. So, why do I say 7? 1, 2, 3, 4, 5, 6, 7. Those are the 7 principal quantum numbers. N. N equal 1, N equal 2, N equal 3, 4, 5, 6, and 7. Okay. Basically your energy level, and it's based on how the average distance from the nucleus. Now, the second quantum number is called the angular momentum quantum number, and that's L. That's not an I, that's an L. Angular momentum, the symbol is usually L. Lowercase l. Lowercase n, lowercase l. This is based on spatial distribution. Not how far from the nucleus, average distance of the nucleus, that's n. Spatial distribution. That's your angular momentum quantum numbers. Now, it doesn't use numbers, it uses letters. S, P, D, F. They list G, H, and so forth. We never go there. Okay, we won't be going there. We're only going to be using S, P, D, and F. Now, where are those? The S's are, for the first N equal 1, there they are, 1 and 2. After that, the S's are right here. The first 2 columns here. Those are the S quantum. They represent that. Okay? The P, second one, those are these here. There's 6 of those. 1, 2, 3, 4, 5, 6. Okay? Then the D. The D's are here in the middle. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you have the F, and the F's are down here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. So, those are your angular momentum quantum numbers, L, and you have 2 in the S, 6 in the P, count 10 in the D, and 14 in the F. Up to 14. Up to 2, up to 6, up to 10, and up to 14. 10 and up to 14. Okay, that's the second quantum number. The third quantum number is the magnetic quantum number, and that's the spatial orientation of the orbit. It's not given a letter. It's not given anything right now. It's just a spatial quantum number of the magnetic quantum number, which is the spatial orientation of the orbit. Now, what that means is, well, I think you'll see it better when we get to it. So it's a little nebulous to try to describe without a little bit more visual. Okay? So, and then the final spin quantum numbers, again, it's not given a letter, but what it is up or down, plus 1/2 or minus 1/2. That's your spin quantum number. Every electron is either spinning up or spinning down. Okay. Those are your 4 predominant, those are the 4 major quantum numbers. The N goes from 1 to 7. The L, letters S, P, D, and F. Magnetic quantum number we'll get to, and spin quantum numbers is up or down, plus or minus 1/2, whatever you want to call this. Okay? Now, your S orbital, okay, it's just one orbital, and it's centered around the nucleus as a sphere. Now, again, this is a distribution. It's not where they are, it's where they could be, okay? It's somewhere there. There can only be 2 electrons in the S's, okay? And they're somewhere in that distribution. Now, your angular quantum number, L, okay, and it's not really a number, it's a letter, S. Here's S. There's P. P is the second one. Now, here is one possibility for P, okay? You can name these any way you want to. I'm going to name this the x-axis, the y-axis, and the z-axis. So one possibility for the p orbital is like this. However, it could have been like this on the y-axis, or it could have been like this on the z-axis. Which one that is, that's your spatial orientation of the orbit. The p orbital is going to be sort of a barbell-shaped thing like this, and you have up to 6 electrons in them, 2 in this one, 2 in that one, and 2 in that one. So that's where you get your 6 possibilities for your P. Okay? The magnetic quantum number is which orientation it is, along the X, along the Y, or along the Z. So magnetic doesn't have a letter or even a number, it's just what orientation it has, spatial orientation. All right. Now, and here, this is showing the 3p orbitals. Now, we move the axis around some. This is your x-axis, so that's one orientation. Here's the z-axis. No, goodness gracious. They put x, y, z. Okay, that's fine. Okay, x-axis, the y-axis, or the z-axis. You can have up to 2 electrons in any orientation. Okay, so that gives you maximum 2, 4, 6. You could only have 1, 2, 3, 4, 5, 6, something, any way like that. That's your 3 possibilities of your p orbitals. Which orientation it is, that's your magnetic quantum number. And it really doesn't have a number that they use or anything. All right? Now, here is your spin quantum number. It's either spin up or spin down. Usually they give plus 1/2 or minus 1/2. Because in an orientation, in a atom, how do you know what's up and down? I mean, there's no way to say it's one to one direction, one to the opposite direction. Spin up or spin down. Okay, so that's why there's 2 always, okay? Always a product of 2. The s orbital, 1 or 2. The p orbitals, 1, 2, 3, 4, 5, 6, okay? And the d's, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the f's, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. Blah, 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 huh? Now, in filling up the periodic table or creating different elements, okay, this is how they do it, okay? In the first n equal 1, you have only s, L equal S. That's the only possibility. 2 electrons possible, so only 2 elements in one S. Okay, two electrons. And the first n equal 1, hydrogen and helium. When you get to helium, that shell is filled. Helium will not react with anything because its outer electron shell is filled. Okay? Then you go over here, start filling n equal 2, S, S1, S2, lithium, beryllium. But you see the second energy level, N, has 2 L's, S and P. So they're not filled until they do the P. And the P has up to 6. Boron, carbon, nitrogen, oxygen, fluorine, and neon. Now when you get to neon, you got the S2 filled, the P6 filled, it's full. No more room. It won't react with anything. All these in the right-hand column, that's why helium is over here rather than here. These are filled energy shells. Nothing reacts with helium, neon, argon, krypton, xenon, and radon. Nothing reacts with them at all. You don't form compounds with any of those. They have filled electron shells, and they do. Everything else, open gate. They react all sorts of ways. So n equal 3, that would be starting here. For the S, you have sodium and magnesium, S1 and S2. Okay? Then you have your P's. The P's would be aluminum, silicon, phosphorus, sulfur, chlorine, and argon. Okay? And that fills that shell. Well, you might say, what about the D here? We're going to get to that a little bit later. Here's the deal. D is actually higher energy than NS, 4S. So 3D is actually higher energy. So we go back and do 4S before we do your, so we do 4S is potassium and calcium. Then you do go back and fill up 3D with 10 more. And that's your scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, and copper and zinc. Okay? You fill up those 10 before you go to your the ones down below. Okay? So it's a little strange there, but I'll show you how you know it. Okay? But this is the maximum you can have. N equal 4, that's the fourth column here, starting with potassium. It's going to fill the 2 S's, that's potassium and calcium. Then you would fill your 6, well, no, okay, potassium, calcium. Then you go back and fill in these 3, I've said that already, I forgot, these 10. Then you go to fill the next 6 over here. Gallium, germanium, arsenic, selenium, bromine, and krypton. Those are those 6. Okay? You don't do these until later. Okay? But that's N equal 4. Can have 2 here, 6 here, 10 here. Those 10 are down here in row 5. Strange but true. You can have these F's. In fact, you do, but you don't have them right away. you have to get on down for a ways, and then they finally do here. Here are the 14 F's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Okay? So these are quite a bit later before you fill these. Don't sweat this. This is just showing you how they fill up. The maximum number of electrons in N equal 1 is 2. In N equal 2 is 2 plus 6 is 8. In N equal 3, 2 plus 6 plus 8, 2 plus 6 plus 10, 18. N equal 4, 2 plus 6 plus 8 plus 14, 32. But that's not the order in which they fill. That's just the maximum you can have in those 4 energy levels. All right. Now, if and when you got down to 5, N equal 5, beginning here, you're going to do S2, but then you go back and do 4D. Okay, you still haven't done the, again, 4D next, and then you go back and do your, 3D. No, I'm sorry, when you're at 5. 4D, then you go on and do your 5P, those are the ones over here, and then you start back over and do 6-2. So we still haven't done any F's yet. So you do 6, 2, and then, rather than hitting your 4D, you go back, 5D, you do your 4F. So that's the lithium series. That's why they put it down here. If they kept making it wider, you couldn't see anything. It'd be way too wide. So they moved the F's down here at the bottom of the page. But lithium fits in right after lithium, you get cesium. Okay, and then you do all these before you go back to, hafnium. So they don't quite have these in the right places, but that's where they always put them. Okay, so you never get to this one until you get way down to 1, 2, 3, 4, 5, 6. Okay, you don't do this one until you're in the 3D until you do 4S, and you don't do 4D until you do 5S. You don't do 4F until you do 6S, and then you start off there. Don't sweat that part. There's an easy way to follow that. Okay? But that's how the quantum numbers go. Okay? Your main quantum numbers, average distance from the nucleus, that's your N's. And they're numbered 1 through 7. Okay? Theoretically, they could go higher, but on our periodic table, they don't. Okay? N equal 1 can only have 2 electrons. Only has 1 sublevel, S. N equal 2 has 2 sublevels, so it can have 2 and 6 or 8 electrons in N. N equal 3 has 3 sublevels, S, P, and D, and it can have up to 18. N equal 4 can have 4 levels up to 32. Okay. The reason everything's even number is always spin up, spin down, spin up, spin down. Always. Okay. Now, let's pause for just a moment here. Okay? Before we go too much further, there's a blurb at the top of page 217 on atomic research. And they list some of the big names and big things that we found out in that. J.J. Thomson investigated cathode rays and discovers the electrons. Robert Millikan measures the charge of the electron. Thomson had only gotten charge of the mass ratio. Millikan actually did the charge, figured out the charge. Ernest Rutherford discovered how the atom is put together, negating what Thomson's plum pudding model, finding out how it really looks. Niels Bohr proposes the solar system model by applying quantum concepts. Remember, you had to have these standing waves for the electrons. Okay? And then Erwin Schrödinger proposes the model of the atom based on the wave nature of the electron, and that pretty much gives us what we have now. They have some questions here. You're certainly welcome to look at those. Now, remember back here, they showed the p electrons, okay, p orbitals. The s orbitals are around the nucleus. The p orbitals are these lobes that go out from there. Okay, there's 3 lobes, one on the x-axis, one on the y-axis, one on the z-axis. I actually have this one backwards, but it's okay. All right, the d orbitals, I can't even begin to show you how that is. There's 5 of them and 2 lobes each, so it's really hard to tell. There it is, though. That's what they sort of look like. 5 sets of lobes, each holding 2 electrons for 10 electrons. And so, anyway, that's a little bit more detailed than this gives. Probably more than you wanted to know. Okay? Now, all right. What's your electron configuration? And this is the second part of the lab on Tuesday. Okay? You will be figuring the electron configuration for 4 different elements. Okay? I think it's 4, something like that. Now, this is the arrangement of the electrons in the atomic orbitals. The principal quantum numbers N, 1, 2, 3, 4 to 7. You won't go up to 7. Angular momentum quantum numbers S, P, D, and F. Okay? We'll stop there. And the magnetic quantum number, that specifies the lobe, which lobe you're in. Specifies the atom's quantum state. Now, a couple of other issues here. Let me see. I need to back up once, okay? Remember, actually back up quite a bit. Remember when I said this doesn't represent individual electrons, this is a probability distribution of where they are. Probability, we don't know for sure, we just have a guess, okay? Along came a guy named, it seems like it's Werner Heisenberg, but I may be crossing it up with somebody else. But his last name was Heisenberg, German, okay? He came up with this thing called, believe it or not, the Heisenberg uncertainty principle. That doesn't sound very encouraging, does it? It says you just don't know. And here's what it says. It states that you cannot measure the exact position of a wave because the wave is spread out. Okay? One cannot specify the position and the momentum of a spread out electron. The location can only be described in terms of probabilities and where it might be at a given level. The probability of the location is described as that fuzzy region called the orbital. And that's why they look like that, because it's only a probability. Now, more specifically, that's a probability cloud, they call them, too. Now, actually what Heisenberg's uncertainty principle is, if you know, or you think you know, the exact position of the electron, you cannot possibly know its velocity. If you thought you knew the velocity, you'd have no clue of the position. So, you may know something, but you can't know them both at the same time. You just cannot do it. That's of electrons and all the other super small particles that make up your atoms. Okay? Now, let's go back then to electron configuration. All right? This configuration specifies the atom's quantum state. Where is the atom? Now, the next guy that's mentioned here, Pauli's exclusion principle. Now, Wolfgang Pauli was an Australian physicist. His summary, now known as the Pauli exclusion principle, states that in your book it says, no two electrons in an atom can have the same four quantum numbers. Impossible to have. Okay? So each element has a unique set of quantum numbers. Okay? There's a maximum of 2 electrons per orbital. Maximum of 2 electrons per orbital, but one of them is going to be spin up and one spin down. So they can't possibly have the same 4 quantum numbers. Okay? It's a little fuzzy to say that because magnetic quantum number really doesn't have a number. Okay? So anyway, the chemical properties are determined by this electronic structure. Okay? Now, I think they do a fairly, let me just see. Yeah, we'll, we're going to come back to chemical properties later. They put it here and then leave it there and leave it hanging. We'll come back and describe what they mean by that. Before we do that, let's write some of these electron configurations. Now, the electrons fill the available orbitals in order of increasing energy. Now, when it comes to that spin up and spin down, that's sort of random. Okay? They do one, then the other. It doesn't really matter. But the others, the 1, 2, 3, 4, the 7, S, B, D, F, all these are according to energy. Okay? Increasing energy. So they're going to show us how to do strontium. And strontium, if you got your periodic table or somewhere in that chapter, strontium is right down here. Number 38, strontium. Okay? It's in row 1, 2, 3, 4, 5, column 2. We'll talk more about columns later. Since it's in row 5, that means the maximum N is 5. It has N1, N2, N3, N4, N5, no further. Okay? And then it will fill according to what we got. So here's what we use. Now this looks a little bizarre, but let me explain what's going on. And I'm going to use the periodic table to help. The lowest energy level is your 1s. So you fill that electron first, that's spin up or down, and here's the other. 1s, 1s1, 1s2. Okay? Then you go to 2s. 2s1, 2s2. Then you go to 2p. 2p1, 2p2, 2p3. Yeah, basically you say that. But 2 of these are on X, 2 are on Y, and 2 on Z. Those are the magnetic quantum states. We don't really have a number, but those are those 6 there. Okay? 2p up to 2p6. No more than 2p6. Then you go down to 3s. 3s is sodium, 1, magnesium, 3s2. Then you jump over the 3p, 1, 2, 3, 4, 5, and 6. Okay. Now, here's the catch. 3D you don't fill until you do 4s. And that's why these arrows are here. And I'm going to connect the dots. They do it in the book. They don't do it on the slide set. So I'm going to connect. You do, I could use red, but I think I'll go to black. You do, well, let's do blue since they have it blue. Okay, that one. All right, you do 1s, and then you come around and go 2s. Then you do 2s, and you come around and do 2p. Then you do 3s, and you come around and do 3p. Okay? But then when you get to 3p, rather than going to 3d, you go down to 4s. That's the next highest energy level. Then after you do 4s, you go back and pick up the 3d, because 3d is actually higher energy than 4s. So that's why you have this weaving mechanism here. So that's why you have the gap here. You see, you did the S's and P's. Then you did S's and P's again, even though you had a 3D. But you don't fill the 3D until you fill 4S. Okay? Then you come up and do 3D. Okay? And these are your 3Ds. Even though they're in row 4, they're the 3D filling. These are higher energy. The Ds here are higher energy than the 3Ds here are higher energy than the 4S's here. Okay? So you fill those 10 now. Okay? And that's why you have that jump. Okay? Then after you do your 3D, you do your 4P. Those are right following that. Then you jump down and do the 5S. 1 and 2. Okay? And that's where you find strontium. Right there. After you fill those two. So how do you write that? Strontium would be, I'll go back to black. Okay? Here's how you would indicate strontium. 1s2, because you got 2 in that one, 2 in every level, spin up, spin down. 2s2, then you go up to 2p6, then you do 3s2, s's can only have 2, and then you do 3p6 again, they can only have 6, okay? Then you go down to 4s, and that's only 2. Then after that, you go back and do 3D. Well, D can have 10, okay? Then you do the 4P. P can have 6, and then you do your 5S. Now, how do you know when to stop? You have to keep a running total. So here's 2, 4, 10, 12, 18, 20, 30, 36, and 2 would be 38. You stop when you reach the atomic number. So this is strontium right here. 1s2, 2s2, 2p. You follow this pattern for every one of them. 2p6, 3s2, 3p6, 4s2, 3p10, 4p6, and 5s2. Stop there because you've reached your 38. So you have to sort of keep a running total. Does that make sense? All right, good deal. So there's how you write your electron configuration. That's strontium. Those electrons. Okay? And there it is when they wrote it. Let me erase my chicken scratch so you can read theirs. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3p10, 4p6, 5s2. Stop there. Okay? You in your lab will do some below strontium. They'll be easy. Then you'll do a few above strontium. They take a little more effort. Okay. Now we start 8.5. Periodic chemical properties. This is going back and picking up where they left off here. Chemical properties are determined by electronic structure. So really that last bullet should have been in a later slide, as in this slide. Okay? These periodic chemical properties are understood in terms of these electron configurations, which we were just describing. The electron, excuse me, in the outer orbits determine these chemical properties. Okay. These are summarized by Ryan coming in. Okay. Okay. So we're still missing Latricia, Mendez, and Ethan. Okay. All right. The periodic chemical properties. The electrons in the outer orbits, those last electrons you did, they determine these chemical properties. And how are these summarized in the periodic table? Well, the rows are called the periods. That's where you get the name periodic table. Row 1, row 2, row 3, row 4, row 5, row 6, row 7. Okay? Now, the columns are the families or groups, because everything in a similar column is going to have a similar outer shell electron configuration. Okay. The first column here is the 1A column. Okay? These are called your alkali metals. Now, they name them metals. They are not very, you wouldn't think of them as very metallic. For instance, sodium is a soft material, not very metallic at all, but its electron configuration is very metallic. Okay? So that's your alkali metals. That would be. Now, hydrogen's listed in 1A. Hey, hydrogen is definitely not a metal, but its electron configuration is like a metal. Okay? But lithium, sodium, potassium, rubidium, cesium, and francium. Okay? Gotta deal with that. Okay? 2A are your alkali earths. That would be beryllium, magnesium, calcium, strontium, barium, and radium. Okay? Jump over to 7A, next to the last column. Okay? Now, here's 7A. That would be fluorine, chlorine, bromine, iodine, and astatine, which I've never used or anything. And then finally, in 8A, these are what they call the noble gases. Now, why noble? They don't mess around with the low lights. Okay? They don't react with anything. Helium, neon, argon, krypton, xenon, and radon. In your incandescent light bulbs, argon. Why? It won't react with the titanium in the filament. No matter how hot it gets, it's not going to react with it. If you had oxygen in there, it's gone. That's why if you even don't do this, but if you take a pin and poke it through that very thin glass in a light bulb, the filament goes like that. Because oxygen gets in there, burns it up in no time. Immediately it'll be dead. Even though the glass didn't crack, you just had a little hole, let it oxygen in. The argon doesn't react with anything. Quite often in dual pane glasses, in really high-end windows, dual or triple pane glasses, they will not just have air in that space between, they pump in argon. So it doesn't react with anything. It won't support bacteria or anything else. It doesn't react with anything. Okay, all those are like that. Now, they only mention those four. Every other group has characteristics. Okay? The A group families, those are 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. These are the ones across here, not the ones down here. Okay? The A group families are the main group and their representative elements. The B group are the ones down here with the D electrons. These B groups are transition elements or metals. Okay? Now here's kind of the difference. This is getting a little more technical, maybe even than the book does. But let me summarize. I want to put this somewhere you can sort of see it. Hydrogen with just that one little electron in its outer shell. That's the only electron it has. It's the only shell it has. One electron. That wants to combine with something else to always have two electrons. That's why H2O. Oxygen has 6 electrons in the outer shell. 1, 2, 3, 4, 5, 6. Okay? It wants 8. So it'll gladly share a hydrogen and another hydrogen. Now it has 8. Hydrogen has 2. They're happy campers. That's why H2O water is so stable, because every atom in there has exactly what it wants. Okay? And that's how chemical things happen. Now, that's in the A group. In the B groups, however, these are your metals, your transition groups down here. What they do, these electrons in here don't tend to belong. You know, they don't say, oh, this is my atom, I'm going to stay with it. No. They form these clouds of electrons that can sort of move. And that's why electricity works. Just about all of your good conductors, not all, but most of them, are in this group here. There's your silver, which is the best one, copper, which is the best. And look at where they're at. Right above and below each other. Silver is the very best conductor of heat and electricity, and copper is number 2. Okay? They tend to group in those columns. That happens to be the 1D column. Okay? Okay. The B groups are the transition elements, or your metals. Okay. And here's their periodic table. Now this is a lot less complicated than this one. Remember the upper left atomic number. 1, 2, 3, 4, 5, 6, 7, 8. That's the number of protons in the nucleus. Which happens also to be, what else? In a stable atom. Not neutrons, electrons. So to be balanced electrically, you have to have the same number of protons and electrons. So that's also the number of electrons in a balanced atom. If it's not balanced electrically, it's called an ion. It's not called an atom. Okay? So this would indicate 24 is how many protons in the nucleus, how many electrons in the shells. Okay? For a balance. Okay? Now, what's the difference between 23 and 51? 51 is the atomic weight. The number at the bottom is the atomic mass or atomic weight. Okay? Hydrogen 1 and 1, that means 0 neutrons. Helium 2 and 4, that means 2 neutrons. Lithium 3 and, can't read that. 3 and 7, that means 4 neutrons. Okay, so the difference between your atomic number and your atomic mass, that's how many neutrons you have. Okay? All right. That's the first part of your lab coming up. So you see how this sort of all plays together pretty well. So, here's what we got. 1A, 2A. How many electrons in the outer shell? That's what the 1 and 2 stand for. 3 in the outer shell, 4 in the outer shell, 5, 6, 7. Okay, let's think back on this 7. It wants 8. So it will rip off of these number 1s. Okay? Sodium chloride. Look at that. What is sodium chloride? Salt. Exactly. This one loses an electron, so it now has 8 in its outer shell, and this one will gain an electron. It has 8 in its outer shell. They're happy campers, but because this was now positively charged, that was negative charged, they hang together really tight by electrostatic attraction. So that's what makes salt a stable thing. Sometimes they share electrons like hydrogen and oxygen. Other times they exchange electrons and make electrostatic, well, they call them electronic bonds, electrostatic bonds, and the others are called covalent bonds. Okay, that's more than what we're doing now. All right. Any questions? So here's your 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. The number of electrons in the outer shell. The transitions, now this is the strange part. 1B, 2B, 3B, 4B, 5B. Why, I don't know. 3B, 4B, 5B, 6B, 7B. The 3's follow from here. The B's pick up here. 1 and 2 here. So 3 pick up there. It's kind of strange, but it's true. And remember, these are good conductors. Gold is a good conductor. Silver's best, copper's next, gold is one of the top 5 probably. Okay? 2B, or not 2B, okay? Then you go over here to 3B, 4B, 5B, 6B, 7B. Now 8B, they do 3 in that. Now notice what's your top row of your 8Bs. Iron, cobalt, and nickel, your 3 magnetic materials. That has something to do, I can't tell you what, but it all depends on this electron configuration. These don't show it, but they get more complicated down here. And these are rarer too. Okay? So, that's your periodic table. Here's your S electrons for the first row. Here's the S electrons for the next. Here's your P's. Here's your D's. And here's your F's. Okay? Wow, it's put together really amazingly. All right. Now, as I just said, the noble gases, those are the 8A's. Filled shells, inert, they do not react with anything. Okay? When you have 1, 2, or 3 outer electrons, they do one of 2 things. They either lose the electrons and become positive ions, or sometimes they act more like metals. Sometimes they'll share electrons. Okay, we won't get into this. The 5 through 7, 5, 6, and 7, the outer electrons, that's through 2A, 2, 5, 1, 5, 1, 6, and 1, 7. Okay, they tend to gain electrons and form negative ions. These are typically nonmetals. These are all metals. These are nonmetals. Now, let's go back in. Oh, here they are. They cut out the D's here. This is just your S's and your P's. Okay? They cut out the D's so they don't confuse them. These are, you call your metals. These are the alkali metals and the rare earth. They don't call them metals, but they are. These then are your basically getting toward non-metals. Now, certainly aluminum is a metal, okay? But it's the lightest metal. That's why they use it in making aircraft and spacecraft and things like that. But then, okay, we'll get into that in a minute. Okay? These tend to lose electrons because they only have 1 or 2 in the outer shell. These tend to hold them. They'll pick them up. Now, most of the time, the gaining and losing is in column 1 and column 7. Column 1 is real easy to lose. Column 7 is real easy to take them. Your 2s and your 8 and your 6s, they do it to some extent, but they tend to share electrons more than gaining and losing. But it's okay for them to say. Now, you have what we call semiconductors. Let's see if they have a slide with that. Yeah. So these are your metals. All the blues are your metals. See, they sort of stair-step down here. Here are your nonmetals over here, the green ones. Here are your noble gases. They don't react with anything. Just throw them out. They don't react with anything. These are your gases, or nonmetals, let's call it, the nonmetals. And these are your metals here. Okay? The things in between are your semiconductors. They're kind of like metals, sort of, but then kind of not like metals. So they tend to form those semiconductors. And Silicon Valley, the earliest semiconductors were silicon. More recently, they use more germanium, and I think that's I can't ever remember how to pronounce that. No, it's arsenic. I'm sorry, I was thinking it was actinium. Yeah, arsenic is a semiconductor, and that's another weird one. Antimony and tellurium, okay? And then that's the other one, actinide or something like that. Acetine, okay? Those are your semiconductors. Intermediate between metals and non-metals. Have a few characteristics of metals, but then some of non-metals, they make your best semiconductors. All right. Now, also things that make semiconductors, you combine that with an oxide, and that makes it an even better one sometimes. Whoa! That's it for the slideshow. Here is your periodic table. The others are in there too. This is your better picture of the periodic table. It sort of combines several of the features of the other ones. This one doesn't even show your alpha electron, SPD, alpha electrons down listing down here. These are lanthanide series and the actinium series. Okay. All right. Now, your table 8.4, I'm not going to reproduce, but it shows you that first column, the 1A columns. Every one of those has a single electron in the outer shell. Every one. 2s1, 3s1, 4s1, 5. The outermost electron is by itself. Now, they do show you a simplified way of numbering these. Remember when we did strontium? Oh, there it is, 38. Right here. And we did 1s1, 1s2, 2s1, did all those all the way down. What they do is take the last noble gas, krypton, and then do krypton plus 2s2. 5s2. That's a lot shorter hand to do it. Okay? So that's what they're doing in this table here. They don't show strontium, but they show the ones right here. Okay? When they're showing the others, the noble gases, they all have filled outer shell. The outer shell is absolutely filled. S2, P6, 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 P6. All of them are outer filled. So what they do, the last one before, helium is just 1s2. Neon is helium plus 2s2 and 2p6. Argon is neon plus 3s2 and 3p6. Okay, so you can do a shorthand like that if you want to. It makes it a little easier. But for the practice, you may want to list them all just so you get the practice of using it. All right. And let me go back to another slide. This is one, they call this the electron dot notation. It just shows the number of electrons in the outer shell. Now, it looks like that's a plus there. That should be a dot. That looks like a plus. It should be, maybe it's just fuzzy. I don't know. But these are just dots. How many electrons in the outer shell? These all have 7, 6, 5, 4, 3, 2, 1. Filled outer shell with 8. Every one of them. Okay. They do mention, did you have a question? Just stretching. Okay. Rare earths. Okay. They mention these, the lanthanide series, and I think they go into the actinide series. They do mention both of them. These are the ones. Whoa. Oh, they don't show the whole periodic table, do they? Here they do. These are these two. Lanthanide series, actinide series. These are actually the first one in this list, and this one should be over here, because you have, these really should be down here, and these here should be up here. Okay, but they just list them this way. Okay, now, these are things that are used. They're rare, but they're usually quite useful and sometimes really, really valuable. Okay, when you're making things, unusual things with unusual properties, you quite often will find some of these rare earths in there. Does anyone know, you probably don't, but just asking, what country probably is the richest in the world in these rare earth minerals?
Africa.
It's in Africa. What country in Africa? Anyone make a guess? Say again? It's sort of west.
Sierra Leone?
Huh?
Sierra Leone? Sierra Leone?
No, it's actually Congo, which is one of the poorest countries in the world. And they have a very sad story. They were colonized by the Belgians, I guess. King Leopold of Belgium. All the other European countries were grabbing up as many as they could. Belgium was lagging behind. He somehow got in there and got the Congo. And he was the very worst of the monarchs to his colonies. He was terrible. And he used the Africans, the Congolese, to be basically, for lack of a better word, his slaves to work in the mines, and he ripped that country off. They got rich, Belgium did, the Congo got poor and poor. Okay? Right now, okay, finally they overthrew Belgium. It was either through in Leopold's time or one of his sons or something. But right now, they're still a very poor country because Belgium never developed an infrastructure for them. They all just ripped them off. Okay? And so there's been infighting, outfighting, really lousy leaders, various things. Right now, guess who is the predominant, it's not really a colonizer, but the predominant non-Congolese country in Congo? China. Because China is trying to scarf up all these rare earths that they can get. And they'll go in there and build highways and just do all sorts of improvements, but they'll bring in Chinese then to do all the thing, and they're ripping off the wealth of Congo again. The factions in there will take anything they can so they can keep fighting with each other, and that's just been the sad history of the Congo. Now, that's way more than you probably wanted to know, and I'm not absolutely certain that all that is true, but that is generally pretty true. Okay. Then, the people behind the science, quite a name here, Dmitry Ivanovich Mendeleev. He was the Russian scientist, chemist, who basically put together the first really good working periodic table. And everything we have now in the periodic table based on what he did. Brilliant chemist. All right. There's another blurb on page 224 on your semiconductors. Well worth your reading there. Your metals and your charge, now they're talking about those clouds of electrons. Okay? The outer orbitals, okay? Some of these are real easy to tell. Some of them are a little harder to tell, but anyway, you can do that. I found that the book is not greatly clear on some of that, but please read the book. What do I say every chapter? Nothing replaces reading the chapters. You'll learn far more than I can possibly relate to you, and certainly way more than the slides will relate to you. So read the chapters, and what you have, there's a pretty good summary here, because we covered a lot of people, a lot of events, a lot of things going on. We did do several equations. They list 5 of them here. The key terms are listed, quite a good list of those. And then applying the concepts, probably the best thing to study for your test. 49 questions, about normal, maybe a few more than normal. The answers are given, but try to do these without looking at the answers, then see how you do. Questions for thought, they have 12. There's a few fewer than normal. 6 is maybe 1 or 2 more than normal for further analysis. A little interesting blurb on invitation to inquiry there. And then you have your parallel exercises, which basically are like the examples that we did as we went along. And these mostly are pretty reasonable ones. I'm sorry, your small books don't have the answers in the back. I specifically requested they put them there. Evidently they did. All right. And this is as far as we go in the chapter. Any questions on chapter 8? Okay? So, Tuesday's lab, after I give back all your labs and all your tests, and you eat all of the pizza, okay? Once all that's done, then we'll start and do Chapter 8 lab. It's a paper lab. We'll do it here in this classroom. You'll use your book and what we talked about and do the lab, filling out one piece of paper, okay? It's one I made up, by the way. All right. Then, after you do that, we'll have the test on Chapter 8. Sorry, they're coming fast and furious now, aren't they? Test on Chapter 6 today, 8 on Tuesday, final exam on Thursday, unless you opt to do 2 tests on Tuesday, which is your option. All right, any questions? Okay, how are we doing on time? Is it 5:45?
It's 4:41.
Oh, 4:41, I looked them up. I forgot to move my clock. Okay, sorry. Yeah, that's right, it's 4:41. Okay, so we've got a full hour of class left, but all you got to do is do your test. So you sure you don't have any questions? Chapter 6 or Chapter 8. Okay? Well, then let me shut this down because we won't need to record during the test.